Welcome to episode 9 of the Semiconductor Age. A modern processor contains billions of transistors. But a transistor is only a tiny switch. So how do billions of simple switches become a machine capable of computation? The answer begins with logic. A transistor can control the flow of electrical current. In digital electronics, we use its two basic states as a switch. Off represents 0, and on represents 1. This simple idea is the foundation of digital computing. Two physical states give us binary information, 0 and 1. One bit has two possible states. Add more bits, and the possibilities grow rapidly. 8 bits can represent 256 different combinations. Simple switches can therefore represent enormous amounts of information. Now we connect transistors together. Instead of simply switching, they can perform logical operations. A logic gate takes one or more inputs and produces an output according to a defined rule. This is where switching becomes decision-making. The basic logic operations are AND, OR, and NOT. AND requires both inputs to be true. OR requires either input. NOT reverses the input. By combining these simple rules, electronic circuits can make increasingly complex decisions. Two particularly important gates are NAND and NOR. They are called universal gates because combinations of them can reproduce every basic logical operation. This means remarkably complex digital systems can be constructed from a small set of fundamental building blocks. A single gate performs one simple operation, but connect thousands or millions of gates, and much more becomes possible. Gates combine into circuits designed for specific functions. This hierarchy, from gates to circuits, is how complexity emerges from simple semiconductor switches. Can logic perform mathematics? Yes. A half adder combines two binary inputs and produces two outputs, a sum and a carry. It is one of the simplest circuits that turns logic operations into actual arithmetic. Real binary numbers contain many bits, so addition must also handle a carry from the previous position. The full adder does exactly this. Connect multiple full adders together, and a circuit can add multi-bit numbers. Addition is only the beginning. By combining logic gates and arithmetic circuits, hardware can perform subtraction, comparisons, shifts, and other operations. These functions come together inside the arithmetic logic unit, or ALU. In combinational circuits, the output depends only on the inputs at that moment. Adders, multiplexers, decoders, and comparators are examples. There is no memory of the past. The same inputs produce the same outputs. But computers also need circuits that can remember. Sequential logic depends on both the current input and the previous state. Flip-flops, registers, and counters provide this ability. This combination of logic and memory allows digital systems to operate step by step. Complex digital systems need coordination. A clock provides a regular sequence of electrical pulses that tells circuits when to change state or transfer data. It acts like a common heartbeat, synchronizing millions or billions of operations across a chip. Now the pieces come together. Logic gates form circuits. Circuits create arithmetic and control functions. These become the ALU, registers, control unit, and other processor components. Together, they form a CPU capable of fetching and executing instructions. From a physical perspective, a processor is remarkably simple at its foundation. Billions of semiconductor switches organized into layers of logic. Transistors become gates, gates become circuits, and circuits become computation. Complexity emerges through organization and integration. We have now moved from the transistor to logic, from logic to circuits, and from circuits to the processor. But what actually happens inside a processor when you run a program? Join us in episode 10 as we go inside the CPU and discover how a processor really works. And if you enjoyed this journey, like, share, and subscribe to Physical Science's Consultorium. Your support helps us bring more fascinating science and technology stories to you. Until next time, keep exploring, keep questioning, and keep discovering.